Hey guys, today we're going to learn about analyzing circuits. So last time we learned about schematics and schematic diagrams and what the individual symbols mean, and we did a little bit of manipulation with Ohm's law to figure out some things about very simple circuits. But today we're going to go into a little bit deeper and look at more complicated circuits. So the two kinds we're going to look at are parallel circuits, which is this ladder type, and the series circuits. Okay, it doesn't really matter what order we do them in, we'll see them both. But what we're trying to figure out in our circuit analysis is as much information about them as we can derive from the given information. Now, these are sometimes called VIRP diagrams, which stands for VIRP, voltage, current, resistance, and power. The ones we're going to be doing, though, the resistance will always be given. So we're just interested in determining the voltage drop, the current, and the power for each of the different components in the circuit, and that includes the battery. And as we get into this, we'll this will all make more sense. Okay, so first off, let's go to this one here. We'll start off with a series circuit since it's convenient. All right, so we have a series circuit here with a 24-volt battery, and then there are 3 resistors in series. That's why it's a series circuit of 4 ohms, 6 ohms, and 2 ohms. And our goal, as I said before, is to figure out how much voltage is used up by each of the resistors, the current flowing through each of the resistors, and the power produced or dissipated by each of the resistors. We are given a 24-volt battery, and then we're also going to figure out the current which is flowing through the battery or that the battery is producing, the total resistance experienced by the battery, and then finally the total power produced by the battery. So lots of information, and we'll see how we do it. All right, so for a series circuit, there's a couple insights we need to have which will make our job a lot easier. And the first and most important of these is that since it is a series circuit, any current that comes out of the battery has to go through every single component. So any electrons that come out of the battery, they're all going to go through this one, and then they're all going to go through this one, and then they're all going to go through this one, and then they're going to come back to the battery again. So this is the first one here. Current is the same everywhere. Current is the same everywhere. Okay. And then the second piece of important information to let us crack this is to remember that when we have resistors in series, we can just add them up to get a total resistance. So it's just like we took a 2 ohm, a 6 ohm, and a 4 ohm resistor. We could just link them together side by side by side and make a single longer resistor and have the equivalent resistance. So that's where we're going to begin. We're going to figure out the total resistance, that the battery encounters. Now, again, you kind of have to remember the battery is just a stupid thing. It's just an object, and it's trying to push electrons down the wire, and it's having a little bit of trouble doing that because of the fact that there are resistors in the way. But the battery has no way of knowing if there's a whole bunch of resistors all stacked up in some strange way, or if there's just one big resistor. All it knows is that there is something down there which is trying to prevent electrons from flowing down the wire. Okay, so total resistance is just the resistance that the battery is experiencing. And in this case, this is going to be 4 ohms plus 6 ohms plus 2 ohms, which is a total of 12 ohms of resistance. That's the first one that we have. Okay, now, since we have voltage, battery voltage, and the resistance that the battery is facing, we can use Ohm's law to figure out how much current the battery can produce under these circumstances. So Ohm's law is I equals V over R. We'll use that one. So I is equal to 24 volts divided by 12 ohms, which means 2 amps. 2 amps of current will come out of the battery. So there it is, 2 amps. Now, we use this insight that the current is the same everywhere, and we say, hey, if there's 2 amps of current coming out of the battery, that means there has to be 2 amps going through this resistor, and 2 amps going through this resistor, and 2 amps going through this one. And now we're set because we have 2 out of the 3 variables that we need for Ohm's law, and we can figure out the other information. So for this one here, we'll use the form of Ohm's law, which is V equals IR. So we have V equals 2 amps times 4 ohms is equal to 8 volts. Okay, 8 volts. Now, what this means is that this resistor is using up some of the voltage to do whatever it is it's doing, to produce heat or light or whatever function it's trying to do. So if we were to take a little voltmeter here and we put the voltmeter across the battery, the voltmeter would read 24 volts because it's a 24-volt battery. But if we put the voltmeter across this resistor, we would see that there is a voltage drop. There's a loss of electrical potential because the resistor has used up that has used it up, and we would see that it has an 8-volt drop across this resistor. So that's what this 8 volts means. It's an 8-volt drop across this particular resistor. Now we can go down to this one here, V equals IR. So we have 2 amps times 6 ohms, which means this is a 12-volt drop. And then 2 amps times 2 ohms is a 4-volt drop. Now I'm going to show you an interesting thing, and this is also a quick check to make sure that we're doing it right. If we add up the total voltage drop, 8 plus 12 is 20, plus 4 is 24. These 3 resistors have used up 24 volts. And they kind of have to because it's a 24-volt battery, and everything it can do, it's going to do. The energy that this thing produces is going to go somewhere. So we can check to make sure we've done our math right by making sure that the total voltage drop in the resistors is the same of the voltage in the battery. And it is, so we know that we're on the right track. We haven't made an arithmetic error someplace. Okay, so now we have the voltage and the current for each of the resistors, and that leaves us just with power. And power, as you probably recall, P equals IV is current times voltage, so we can do this for each of them. P equals IV for this first one is going to be 2 amps times 8 volts, which is 16 watts. So this one is dissipating 16 watts of energy. 16 joules per second. This one down here is 12 times 2 is 24 watts. This one here is 4 volts times 2 amps is 8 watts. And so for the total power, we actually now have 2 ways to solve this, and we should do both of them, again, to give ourselves a backup that we've done it right. So one way to do it is just to add up the power that is coming out of the resistors, because the power that comes out, or the energy that comes out of each of these resistors, has to have been coming from the battery because that's our source of energy. And energy, as you know, has to be conserved. So total power is equal to 16 plus 24 plus 8, which equals, let's see, that's about 48 watts. Believe that's right. Yep, 30, 48 watts. Great, so this is going to be 48 watts. But this doesn't give us a backup to make sure that we haven't made a mistake somewhere and just carried it into the final thing. So we want to back this up by seeing the voltage of the battery times the current coming from the battery, because the power produced by the battery is its voltage times its current. And that's 24 times 2, which is also 48. So we're calculating the power 2 ways. First, by adding up the individual powers from each resistor, and then doing the calculation for the battery itself. And if they're the same, which they are in this case, then we can be pretty sure that we've done the rest correctly. Okay, so series circuits. To summarize, to begin, we recognize that the current is the same everywhere, and that to calculate the total resistance, we just add up the individual resistances. So when we add up the individual resistances, that's the resistance that the battery is facing. Then we calculate the current coming from the battery based on Ohm's law, and then recognize that that current is going through each of the components and then we're off to the races. Okay, that's series. Now let's do parallel. So here's a parallel circuit. As you recall, in a parallel circuit, we have more than one possible path for the current to take, for the flow of charge to follow. But still all of the power and the energy is coming from the battery. So in this case, we have a 36 volt battery going through 9 ohms, 3 ohms, and 6 ohms set up in parallel. Again, we want to figure out the voltage drop across each one, the current flowing through each one, the power dissipated by each one, and same information for the battery. The current that the battery is producing, the total resistance faced by the battery, and the total power produced by the battery. Now, the insight that we need to have for the parallel circuit is that the voltage drop is the same for each component, for each resistor. Now, why is this? And we actually touched on this a little bit last time. The idea is that, for example, with this individual resistor here, all it knows is it has a direct path to the battery. Current leaves the battery, goes through this resistor, goes back to the battery. As far as this resistor is concerned, it's the only game in town. It has no awareness or concern with any of these other resistors down here. So that means that this resistor is encountering 36 volts. And the same thing is true for this one. It has a direct path to each terminal in the battery. So the voltage drop across this resistor is 36 volts. That's the same for everything. 36 volts, 36 volts. Okay, I put the power off to the side on this one because I didn't want to go off the bottom of my screen. Anyway, now again, we're off to the races because we have 2 out of the 3 pieces of information to feed Ohm's law for each one of our resistors here. So again, we're going to use Ohm's law, I equals V over R. And for the first one here, I equals V over R is equal to 36 volts divided by 9 ohms. And that is equal to 4 amps. 36 divided by 9 is 4 amps. So this is 4 amps. We do the same thing for the others here. 36 volt divided by 6 ohms is going to be 6 amps. And 36 divided by 3 ohms is 12 amps. All right. So now we have 2 out of 3. Now, for being able to figure out these things, again, we have to have another insight. And that's that all the current or the charge that makes up the current is conserved. Again, it's like water flowing through a manifold of pipes. This is the pump. It's putting out a whole bunch of water, and some of the water takes this path, and some of the water takes this path, and the rest takes this path. But that means that the total current flowing through each one of these has to be coming from and going back to the battery. So we can figure out the total current through the battery by adding up the individual currents in each of the components. So we have 12 plus 4 is 16, plus 6 is 22 amps. 12, nope, 16, yeah, 22 amps, 22 amps. That's the current through the battery. Now, for the total resistance, we again use Ohm's law because now we know the voltage of the battery and we know how much current it's able to push. And the relationship between these two will reveal what the resistance is, the resistance that the battery is encountering. In this case, this is going to be 22 amps is equal to 36 volts divided by the total resistance. And that's going to be 36 divided by 22 comes out to be R equals 1.64 ohms is the equivalent resistance that the battery encounters, 1.64 ohms. Okay? Now I'm going to show you another way to solve that so we can back ourselves up and make sure we haven't accumulated errors somewhere along the way, but we'll come back to that at the end. I do want to show you how to solve the rest of this. Okay, now power. Same as before. Power is current times voltage. So for this one, it's going to be 36 volts times 4 amps. I don't want to mess this one up. So 36 times 4 equals 144 watts. That's 144 watts. This one is 36 times 6. 36 times 6 equals 216 watts for the bottom one. And then finally, 36 times 12 amps is equal to 432 watts. Okay. Now, once again, we have two ways to calculate the power, and we should do both to make sure that we haven't made a mistake somewhere. So the total power is going to be 144 plus 216 plus 432, and that equals 216 equals 792 watts. That's all very nice. That's what we get by adding together the individual power. And then we can also calculate it by taking the battery voltage times the total current. And we get 36 times 22, and that is still 792 watts. So we've calculated that two different ways, and we've gotten the same answer both times, so we can be pretty sure that we've done everything right. Now, how can we check the total resistance here? Now, if we want to find the equivalent resistance of the whole circuit for parallel, the equation is a little bit more complicated than just adding them up arithmetically like we could with the series circuit. So here's the equation. It's 1 over RT, which is the total resistance. So the inverse of the total resistance is equal to 1 over R1. So 1 divided by the resistance of the first one, plus 1 over the resistance of the second one, 1 over R2, plus 1 over R3, and so on for as many resistors as you have in parallel. Okay, so to summarize here, we are taking the inverse of each one of these and then adding them all together. And when we add them all up, we get the inverse of the total resistance. So we're going to be using our inverse key, our 1 over x key, or our x to the minus 1 key quite a bit here. So let's do this. It's going to be for 9 ohms, 3 ohms, and 6 ohms. I'm writing them here because I'm going to be covering this up with the calculator so there's not too much glare. So we'll do 9, 1 over x, plus 3, 1 over x, plus 6, 1 over x equals. So 0.611111 is the inverse of the total resistance. So we have to take the inverse of that, and we get 1.64 ohms. So we did it right. One thing I will point out, this is a final check to make sure that we have it right. Notice that the total resistance for the parallel circuit is less than the smallest resistance in the circuit. So the smallest resistor in here is 3 ohms, and the total equivalent resistance is less than that. And this kind of makes sense because, again, if you think of it as plumbing, a sequence of pipes. If you have just a single pipe here, which 3 ohms worth of resistance, that means it's got a fairly small diameter and it doesn't let very much water through it, right? Okay. But if you open up another pipe, even though it's an even skinnier pipe, it's a smaller diameter than this one. It's still going to let in a little bit more water. It's going to let a little more water flow through, which means that more water is going to be coming from the pump, if you will. So the equivalent resistance, the equivalent of how big or how small the actual pipe is, that resistance, total resistance, will be smaller than the smallest resistance in the resistance in parallel. In contrast, for a series circuit, the total resistance is always going to be larger than the largest resistor in the circuit, because each individual resistor is making it smaller and smaller and smaller, making it harder for the current to get through. Okay, so one final check on the reasonableness of the answer that you get. Okay, so that's what we got today. You've got worksheets to do to practice these skills. a couple of each. I would recommend that you do a parallel circuit analysis and then a series circuit analysis today while this is fresh in your mind, and then set them aside, and then tomorrow or the next day, do the other ones. So do one, sleep on it, and then do the other one. Okay, thanks for your time, and we will see you next time.